afternoon, everybody. Thank you, everyone, for joining us for another EI Live K-12 session for students and educators, a series of the Columbia Climate School. My name is Christina, and I'll be facilitating the session today. For those of you unfamiliar with the Columbia Climate School or joining us for the first time, we are a newly established school at Columbia University for transdisciplinary climate research. The school marshals the university's strengths in basic and applied disciplines and expands its resources to understand climate and its impact on society. The Climate School is the first new school at Columbia in over 25 years and incorporates the entire Earth Institute, which includes the Lamont-Doherty Earth Observatory, along with more than 20 other centers and several hundred people who collaborate among many departments at the university. What we are hoping to do with this EI Live K-12 session is introduce you all to our interdisciplinary work through our scientific experts. These bi-weekly sessions will run through the whole semester, and if you would like any more information about the sessions, do not hesitate to contact us. Each week will focus on a certain topic and will be directed towards a certain age range. Today's session is using tools to explore the changes of the polar regions. We will hear about the dynamic polar regions and the way ice is constantly changing and flowing in response to forces like climate change. We are joined by speakers Margie Turrin, Director of Field Programs, and Laurel Zaima, Education and Outreach Coordinator, both of the Lamont-Doherty Earth Observatory. We'll have time for questions at the end, and please use the Q&A box as the chat has been disabled. It should be on the bottom toolbar. The session is being recorded, and we'll send participants a link for the recording after it's been completed. So without further ado, I'll hand it over to Laurel.
Thank you so much, and welcome everyone. We're so excited to be here to share a little bit about our Eyes in the Sky session today. So we're going to be looking at these different tools that you can use in the classroom or explore at home to explore the changes that are happening in the polar regions. And these are the same tools that can also be used to explore changes elsewhere in the world as well. And they are made possible through remote sensing, which is the way that scientists are able to learn about Earth's dynamic processes. So first, we want to go over some of today's essential questions that we're going to be answering through a series of demonstrations and activities. So kind of tuck these in the back of your head as we go through the presentation today. So first, what drives change in Earth's icy areas? How quickly do these polar regions respond to change? And do certain processes enhance ice loss or ice flow? How can we monitor Earth's changes? And how are humans a part of Earth's system? So you guys can kind of tuck these away. If you have a piece of paper and would like to jot these down, we're going to be reviewing these through activities. Now, it's my understanding that the chat is unfortunately disabled, but maybe if you would like to use the Q&A button, you can type in some different ways that just pop in your head right away about how the Earth is dynamic. There are a variety of ways that the Earth is constantly changing. If you have any that you want to share, you can feel free to do that now. If not, you can just kind of think about these different processes. One way is through the changes in ice. So we are going to be looking at both poles today, so the Arctic and the Antarctic, but the basis of this session is based off of a Greenland project that's actually observing these surface lakes and how it can influence ice dynamics. So since we're talking primarily about Greenland, we want to jump right into what Greenland looks like and where it is. So this is a satellite image of Greenland. As you can see, the Greenland ice sheet covers about 80% of the land mass, which is over 1.7 square kilometers. So it is a huge, expansive ice sheet. Only pretty much the fringes of Greenland are exposed. Now, this map is actually looking at the bedrock topography. So these cooler colors are actually below sea level, and these warmer colors are increasing in elevation above sea level. The first thing that really pops to me, and maybe to you as well, is that the center of Greenland is actually pushed and depressed below sea level. And that's because this ice sheet is so thick and so heavy, especially in the middle of Greenland, that's actually pushed the land down to actually about 400 meters below sea level, whereas the thinner areas of the ice sheet have not had that same influence of depression on the land, and so they are above sea level. So that is really fascinating to look at how the ice has really formed the bedrock and had its influence on the bedrock here. This image is looking at ice flow. So increasing in flow speed are these blues and pinks, whereas slower speeds are yellows. But ice is constantly moving, and that might be surprising to some of us because we always think of ice as a solid. But when ice is this large ice sheet or glacier, it's actually flowing through the force of gravity. So you can see that towards the edges of the Greenland ice sheet, you can see these fast channels or flowing rivers of ice that are actually moving faster than some areas that are a little bit slower towards the center of the Greenland ice sheet. And finally, this image is looking at ice thickness. So reds are very, very thick areas, whereas the blues are a little bit thinner. Right away, you can see that thick area of ice in the center of Greenland, and it reaches about 3,000 meters thick, and then it starts to thin out towards the edges. So these are some basics of the Greenland ice sheet that you'll want to keep in mind as we go through some of these activities. All right, so our first series of activities, it's called Bergie Bits. We're looking at how we're looking at glacier physics and how ice actually moves and flows. And so this is a great activity that you can do at home or with your students in the classroom using something called Glacier Goo. We can share a complete packet of different physics activities as well as instructions on how to make Glacier Goo with you at the end of this session. But the first, we're going to do two of these multiple activities. And the first is going to be looking at how gravity drives ice flow. So what you would do is you have a completely flat mat board with a grid on it, and mounding up that Glacier Goo into a ball, you're going to put it flat on that board and draw a circle around the Glacier Goo. Now you would have, you would want to make a hypothesis on whether you think that mound of Glacier Goo is going to extend beyond the circle that you have drawn, or if it's going to stay within the confines of that tightly circle that you have drawn. And what this really is looking at is the force of gravity on ice. And this is something that it's happening in glaciers all around the world. So, you know, gravity is pulling objects toward it, and the same goes for ice. It's pulling this ice downhill, but even if it's on a completely flat surface, gravity is pulling ice from its highest area to lowest. So even a mound of ice is going to feel that force of gravity. So you can go ahead and make a hypothesis on whether you think it will stay inside or outside of the circle. And we are now going to observe what happens. So I've mounded my Glacier Goo. I drew a circle around it. And you can see that Glacier Goo is moving under the force of gravity from the highest to lowest point and starting to flatten out. And here is another view just to prove that when you pick up your Glacier Goo, how much it is extended on the outsides of that circle that you have drawn. So you can very clearly see that gravity plays a role on ice and how it's flowing from points of highest to lowest elevation. All right, our next activity is looking at basal friction. So in this, you'll take your Glacier Goo, ball it up, put it on a declining ramp, take a toothpick, stick it through the Glacier Goo to the very bottom until it touches the mat board. And you're going to make a hypothesis on whether you think that the toothpick will tip up as the Glacier Goo is flowing down, or if the toothpick is going to tip down. And what mechanism is making the toothpick tip in either direction? Which part of the glacier is flowing faster, the top or the bottom? Now, this is really looking at basal friction. So basal means the base of something, or the bottom layer. And so for this, it's referring to the bottom of the glacier and the friction that it has against the bedrock. So in looking at this activity, You can see the glacier goo is placed on this declining ramp. The toothpick is going right through it. And as the glacier is flowing down, the toothpick is starting to tip downward. So if that was your hypothesis, you're absolutely correct. The toothpick tips down. Now we also want to think about what that means. So knowing that there's friction between the bottom of the glacier and the bedrock, and then it's slowing down the movement. If this toothpick is tipping downward, it means that the top of the glacier is moving faster than the bottom of the glacier that has that force of friction because it's interacting with the bottom of this mat border bedrock. So this is actually a process that's also happening in real life, happening to glaciers around the world. There's other forces of friction that are also playing a role on glaciers that you can explore in some of the other Bergy bit activities. And if you even wanted to look at some of the speeds of how glaciers flow around the world, you can also, there are a couple different activities that go along nicely with the Bergy bits that we can share as well. Okay, so we're going to our second set of activities. This is exploring global glaciers all around the world. We have a set of 5, but for the sake of this demonstration, we're only going to be focusing on 2, and that's Pine Island Glacier and Jakobshavn. And the point of this activity, so we just learned through their Bergy bits that ice moves, that ice is dynamic. This activity is looking at the different speeds of how glaciers are flowing, and that they are flowing differently, and there are different shapes of glaciers around the world, just that there's diversity. So we are going to use Google Earth as a tool for this. Okay, so if you've never used Google Earth before, it's a web-based platform. It's become very user-friendly in recent years. So we are first going to be observing Pine Island Glacier. And there is a series of questions and activities that you can go along with this tool for your students to explore and answer the questions as they go along. But I just wanted to zoom out first to show you that Pine Island Glacier is at the bottom of the world in Antarctica. And if we zoom in, this feature allows you really to see the glacier and even some evidence of its movement. So using Google Earth, there is a tool that allows you to measure different distances on the platform. So while we're looking at Pine Island Glacier, we first want to identify where this glacier is flowing and emptying into the ocean. So this is a natural process. Since glaciers are flowing, a stable glacier has an equilibrium between the amount of ice that's lost from flow and then dumping into the ocean, as well as accumulating through snow and then compacting into ice. So if you have that healthy equilibrium, the ice loss and the ice accumulation would be balanced out. So this is the Pine Island Glacier that's emptying into the ocean, and we just want to measure about the distance of where the mouth of this glacier is, where it meets the ocean. And this could be variable depending on where your students or where you are going to choose a start and ending point. So if you have an entire class of students, taking an average of all their measurements would be the best case scenario here. But what I'm seeing is about 41, 42 kilometers. So that's actually quite a large mouth, or quite a large emptying area of all of this ice. And it's hard to tell from this image, but Pine Island Glacier is actually very steep, and it also has this very wide mouth here. So keeping that in mind, you might want to jot some of these notes down because we are going to compare it against the Jakobshavn Glacier. So using our Google Earth tool here, we're going to go to our other pole in Greenland and look at this glacier to compare. Perfect. So we are now in Greenland. I'm going to zoom into this glacier here. And there's a couple things I want you to just pay attention to, that when we really zoom in, at first it may look like the mouth of the glacier is towards this far western edge. But when you zoom in, you can actually see that this is melange, which is this mixture of different types of sea ice or ice rubble. So the emptying point of the glacier, or where the land kind of cinches this emptying point, really has retreated up to this point here. So for this demonstration, if I were a student, I would actually take my measuring tool and measure from this point maybe to about there. So 10 kilometers, that is significantly different from what we had just looked at Pine Island Glacier. It's much smaller. And again, you can't really tell from this image, but Jacobs 7 Glacier is much less steep than Pine Island Glacier. It has more of a flat elevation as it's emptying out, whereas Pine Island empties down a steeper area. So based on these two pieces of information, that Jacobs 7 has a more narrow mouth, less steep, whereas Pine Island is more steep with a wider mouth, which of these two glaciers do you think would be flowing faster? I see that the chat is working, but I haven't been keeping up with it. So let's see, the tall and the steep. I think that would be my hypothesis as well, that with a wide mouth in such a steep area that it would be flowing faster. But in fact, the Jacobs 7 Glacier is the fastest flowing glacier in the world. And it's flowing at about 34.5 meters per day, whereas Pine Island Glacier is flowing about 9.5 meters per day. So it is fascinating that it has a much smaller mouth, but it's flowing almost 4 times as fast, which is shocking. And there's a couple different processes that are playing in why this is flowing so fast. We're going to look at a couple a little bit later, but this is also a nice opportunity to allow our students to hypothesize, why might this glacier be the fastest in the world? What different Earth mechanisms are driving this ice flow? Okay. So we just looked at how these two different glaciers are extremely different and that the ice is flowing at different rates, different speeds. Now we're going to use this other very cool tool that's made possible through remote sensing as well, called Google Time Lapse. So this is allowing you to look at an area in the world over a series of a certain time period. So we're going to zoom in again on the Jacobs 7 Glacier that we are just looking at, but from this tool here. Okay, so here we are. It's going to start from 1984 and end in 2020. So I'm going to let this run maybe once or twice, and I just want you to observe the changes over time. And then we'll really zoom in at these two starting and ending time periods to look at some big changes. Perfect. Okay, so it just ran through twice. I just want to stop at 1984. So this is where we start our time lapse. It looks like there is some of that more ice rubbly area, but the extent of the glacier is much farther than it was in our Google Earth activity. But when we click on 2020, you can see that the glacier has retreated, and a lot of this is that more of that ice rubble. And so this glacier is not only flowing the fastest in the world, but it's also retreating, which means it's shrinking back. Now, as I mentioned, glaciers naturally flow and ice is naturally lost. But in a stable equilibrium environment, you would have a balance between ice loss and ice accumulation. Through this 36-year period from 1984 to 2020 and beyond, honestly, we have seen that this glacier and glaciers around the world have been retreating back. And it's not just that they're retreating, but they are retreating at an accelerated rate. So I'm just going to share this graphic so you can see that a little bit more clearly. So this illustrations going back, or this satellite image with some markings here is going back from 1850. You can see that this glacier has retreated through time, but the amount that it has retreated has also increased, which shows that it is accelerating. So this glacier is responding to a warming Earth, to climate change, and there are some other processes that are driving some ice dynamic changes as well that Margie is going to touch on.
Great. Thank you so much, Laurel. That was a great introduction to different parts of Greenland. We're going to go to an entirely different process now. We're going to look at the surface of the Greenland ice sheet. We're going to look at some of the hydrology, so some of the water movement. I know we don't think about an ice sheet having water movement, but in fact, both of our polar ice sheets do have some water that moves under and moves through them. So we're going to start with two different images. So this is an image that was collected, and there's a little map down here that you can look at to kind of orient yourself. It was collected in the southwest part of Greenland, England, from Kangerlussuaq, which is a fjord, and it's an area that anyone that's been to Greenland to do research is probably fairly familiar with, from the US anyway, because that's where one of our home bases is. And this is taken 80 kilometers inside of the edge of the ice sheet. So we're 80 kilometers in, and I want to just point out that the width of the Greenland ice sheet is about 1,100 kilometers. So, and that's at its widest. So we're not actually at the widest, but still there's a pretty big expanse of ice there. So 80 kilometers in would still be towards the edge. And what I want you to look at are these two little dark areas that are kind of poking out. They're little bits of blue that are showing us little bits of frozen water that are underneath this surface layer of ice. This is in the beginning of the season. And then we're going to pop to the next image. And we're going to show you that, wow, we're at the end of the season. And this is the exact same satellite projection down. And we're just seeing what's happened during that period of time. You'll see these beautiful meltwater channels that run all over the surface of the ice sheet. And then how these little ponded areas form where this surface water accumulates. And of course, those ponded areas and the channels themselves are a darker color. And so they're going to be more absorptive. We call that albedo. Albedo is the reflectance. These are going to be less reflective. They'll pull in heat energy and they'll start to cause more melt. So it's a positive feedback. And this is a process that goes on, as we just noted. So our evidence here is that this happened in lakes in the southwest on the flank. And also we have evidence that it changes through the course of a season. And so what we're able to say is that this Greenland ice sheet is changing over a seasonal time frame, okay? So we've seen that one. Now we're gonna move to the next set of slides. Again, these are two slides. This is back up by Jakobshavn, where Laurel just took us a few minutes ago. And again, we have some satellite images. You can see on the map that's superimposed on top of this image that Jakobshavn is further north. So we now are moving to a different location, a little bit higher up on the Greenland ice sheet. So potentially climates might be a little cooler. And these were collected in actually in just a couple of weeks. So July 21st and August 1st in 2019, it happened to be a year where it was fairly warm. There wasn't a lot of fresh snow that was added on the surface of the ice sheet. And so what we can see, we can certainly see that there are these beautiful blue images, and it's harder to see the channels that connect them, but if we zoomed in further, I'm sure we would see some of that channel connection. But I want you to focus on this section which says Melt Lake, and we're going to pop to the next image, which is going to be August 1st, and you'll see that that little lake suddenly disappeared. It's drained, it's gone away, and that's a process that we're going to tip into in just a bit. But I also want to point you to this bottom section, Enlarged Melt Lake, and I want you to go back maybe, Laurel, to show them what was down there before. So that was 10 days earlier. Now we're going to go 10 days later, and you'll see that that lake is enlarging. So now what the evidence is telling us that is that this is actually occurring not just in one location in Southwest Greenland, it's actually in several locations. So we know that this is not just a locational situation, and that it can happen more rapidly, right? So this is now happening over a 10-day period versus a 2-3 month or seasonal period. Okay, so now we're going to move to our next set of satellite. Oops, we're not doing satellite images. Sorry, I got ahead of myself. Okay, we're going to go to a set of data, and I'm going to spend just a minute talking you through this data. So this is looking at locations of these small lakes that form on the edge of the ice sheet that we've just been looking at. And we're going to be looking at them in terms of walking through time. So our x-axis is taking us from 1971 all the way through to into the future to 2060. And our y-axis is taking us in elevation, up in elevation. So the base is sea level, and we're going all the way up to 2,200 meters above sea level. Remember, there's about 3,000 meters of Greenland ice elevation at the center. So we're looking at a pretty good subset of that. And what we're going to do, well, first of all, I want to tell you this is a combination of data and then a model that was developed from that data. The data was collected from 1971 to 2012, and the data is represented in those little black hatch marks that kind of go down. Yeah, right. Thank you, Laurel. And so what you'll see is that starting in 71, the length of that line tells us the number of lakes that were counted. And then we jump forward to another set of data that was looked at through using satellite imagery in 1985 or so. And then we move forward to the more recent time, which is where they were really interested in kind of focusing on what's going on more recently. And you'll see that the lakes are moving up in elevation. So thinking about that Greenland ice sheet, and I put that little elevation map down here on the bottom for you, the center is higher in elevation. So we're moving from those flanks where we looked at the last two sets of images. Now we're seeing those lakes are actually moving up in elevation. And the data that was collected from 1971 to 2012 showed that they were spreading inland. So they spread inland by 53 kilometers, which of course, those two things would be correlated. You're moving inland and you're going to move up because of the slope of the ice sheet. So that's the data was collected. Then the purple lines are the model that was developed from that. So the wavy lighter purple line is the whole run. And then those darker purple lines is actually showing you the trend line as to how that's working. And so kind of looking at this and seeing what we see, we can see that there's evidence that these lakes are actually moving higher in elevation and moving into the interior. And so our takeaway is that more of the ice sheet's being affected, and that we could predict that this is going to be happening more in the future. And I know, again, this graph might be a little bit tricky for some people to try and interpret, especially in a really quick introduction. So there is a simulation, which is on the next slide, and we're going to run through that. That looks at these lakes, and now you can see them kind of popping up the surface in elevation. So this is running from 2002, I think it was, up through 2060. And you'll see just how they creep up the ice sheet. We'll let it run one more time, but you can really see this play out in the simulation. And of course, you know, we would expect that as you're moving higher up in the ice sheet, that was a more stable piece of ice. It would have been cooler in temperature, and we wouldn't have expected to see these changes as we're seeing them now and moving into the future. Okay, we're ready to move on to our next set of slides. So this is a series that we're going to look at. This is looking at June. So the image you're looking at right now is June 3rd. The next one we're going to show you is July 4th. And the final one is August 17th from the year 2010. And this is all collected from NASA's one satellite, so our Earth Observer satellites. And I want you to look towards the top right of this, and you'll see that there's a meltwater channel. So again, there's a lot of water that gets moved through these meltwater channels. In fact, there's more water flowing in these channels than sit in the lakes, but it can be deceptive because the lakes collect and pool them. And so they look as if there's a lot more water there, but actually there's a lot more water flowing in these channels. And that water is moving down and it's kind of bowling in the top corner and then moving again and bowling in another corner. And this, I think of it as kind of like a string of pearls across the Greenland ice sheet. There are these little connectors and then this kind of pearl and a little connector and a kind of a pearl. And what we're going to do is look at, oh, first of all, I want to point out the scale bar on the bottom. So the scale bar shows you that it's 500 meters. So these are not small and significant features. Some are much, much bigger than others. So we're going to do this step through. We're going to look June and then we're going to click to July 4th. So a month later, and you can see how much more water has kind of pooled into this area. And now we're going to go to August 17th. So about 6 weeks later, and boom, what's happened is that this base area at the bottom of the bowl where we had the biggest collection of water has actually drained. And what's left now is just this little remnant of water that's sitting collected at the top. And so how fun is that? So we really see how in the world did this drain? There's this very interesting feature that's part of this larger hydrologic cycle on the Greenland ice sheet that's called a moulin. And so these are areas that get kind of forced open by the weight of the ice. They find a weakness in the ice sheet, and they actually have the ability to move water from the surface down to the base in just a matter of, a short period of time. Can be minutes to hours. It just really allows it to move quickly. And when you think about that, if you had to melt your way through that whole ice sheet, it could be thousands of years, whereas you can actually get that water down to the base. So we're going to show you a short movie of one of these in action because you have to see it to believe it.
He threw it straight into it.
Oh.
He didn't even give it a little float time.
Oh, much better.
Roll the dice, feel the fear in my enemy's eyes. Listen as the crowd would sing. Now the old king is dead, long live the king. 1 minute I held the
Second year, this was dry. So we should try. First round maybe more in the middle, and then later we should try to get one
Into that hole. Yeah.
wild wind blew down the doors to let me in. Shattered windows and the sound of drums. People couldn't believe what I'd become. Revolutionaries wait for my head on a silver plate, just a puppet on a lonely string. All who would ever wanted a king. I hear Jerusalem.
I like that song too. So this is first of all, there are a couple of take homes there, and one is what it's like to try and do Greenland field work, and it is extremely challenging. Normally, all those people would be roped in. I think perhaps we didn't see some of those ties, but it's very it can be very dangerous to work around the moulins and the meltwater channels. So they're very, very careful, and all of our funding agencies are very cautious and making sure that safety protocols are followed. So I did want to point that out. And also they obviously have a sense of humor with their little rubber duckies. So they were interested in understanding where that water was going and how quickly it moved through and kind of understanding the physical properties. And so we'll take you to kind of a diagram of this. So this is like a sectional, if we cut through the ice sheet, and we can see, first of all, the EQ line is the equilibrium line. So that's where we would expect to see accumulation on the upside of that on an annual basis, and potentially some annual melt on the lower side of that. That is not a fixed point, obviously. So accumulation lines can move, or equilibrium lines can move. They are, as we've seen, things are moving further into the ice sheet. So we would expect that perhaps that equilibrium line will be moving back with us. And we are seeing that it is. You'll see these moulins on the surface. Crevasses are areas where the ice is kind of pulled apart, and there's certainly something to pay attention to in Greenland. It's and in Antarctica. It's part of a normal feature in an ice sheet, but as ice moves more quickly and as it gets softer, those crevasses can be more challenging. And then you'll see this wonderful diagram where this water empties into a lake, comes in from these surface channels, and then exits quickly down to the base of the ice sheet. And then that really kind of addresses this phenomenon that Laurel was talking about earlier with basal friction, and how it just relieves that basal friction. So Laurel, if you do one more click, yep, it lubricates the bed and it kind of releases some of that friction and helps things to move more quickly. So we've just talked about a whole bunch of different processes, all of which are happening now, which really show us about the dynamism and the changes that are going on in the ice sheet, multiple interactions. So we did quickly talked about some feedbacks, but there are many, many more that we didn't have time to talk about. We talked about how important it is to have these wonderful tools. Almost everything we did related to satellite data, and that is such a valuable tool for us to be able to use in both research and education, and phenomenal. And then we didn't really spend a lot of time talking about how humans are part of the Earth system, but I never like to have a presentation or give a talk where we don't acknowledge that we are definitely part of the Earth system and are having an impact, and it's important for us to pay attention to that. So with that, we will say thank you. I know that the chat's been busy. I've been seeing it fly by, and we can happily address some of those questions and turn it over to our NASA friends to take over now. Would that make the most sense? Great.
Thank you, Margie. Hello, everyone. Can you hear me? Okay. Let me share my screen. Can you see my PowerPoint now? So, yes, hello, everyone. My name is Rosalba Gerratano. I help support NASA's Office of STEM Engagement at the Carter Institute for Space Studies in New York City.
Sorry to interrupt, but we can't see your slides.
You cannot see my slides? Okay, let me try again. Can you see it now?
Yes, perfect.
So, so I am here today to share about some NASA resources, some supplementary resources and tools that may be helpful to you to continue exploring today's topic. So I would like to put some links on the chat. Please do let me know if you don't get them. Once I share my screen, it doesn't show me the chat. I apologize. You know what? I think I may have to do that at the end because it is not letting me see the. One second. Probably here. I don't know if you can see that there. Can you see my links now?
Yes, they're in the chat,
Okay,
but
great. Sorry about that.
I will copy them for attendees.
Thank you. So the 4 resources that I want to share with you today are Global Ice Viewer, Images of Change, the Rise and Fall of Ice Age Glaciers, and Climate Quizzes. Are you still able to see my screen? I'm sorry. Yeah, okay. So the first resource, Global Ice Viewer, so it's basically a series of visualizations about how climate change has affected the glaciers, sea ice, and continental ice sheets worldwide. So for example, if I go to Antarctica, I hope that it opens quickly. So this is the tool. So for example, here on the Antarctica, you can click on the map and look at, this is just an example. Here you can see the ice shelf disintegration that is happening on the eastern side of the Antarctic Peninsula, northern tip. But there are many more visualizations and animations and images. The next resource is Images of Change. So this is a gallery that features images of different locations of the planet so that you can see some very, very dramatic changes. Some of them have to do with climate change, some do not. But the one that I wanted to highlight just as an example is this images of a glacier melt in Greenland. Loading. And so something very cool about this tool is that you have this slider bar so that you can see the same spot on the planet and how it has changed. In this case, for this glacier melt in Greenland, the images are from May 2001 versus June 2005. But again, there are many other images that you can look at with this tool. The third resource is an animation entitled The Rise and Fall of Ice Age Glaciers. It's an animation from NASA's Jet Propulsion Laboratory. And so basically here, NASA software engineers let you pretend that you can turn back the clock for about 122,000 years, and it's as act as if you could place cameras on top of the poles and look at how the ice sheets thinned and thickened over time. And finally, there is another resource. So the NASA's climate site has many quizzes. There are interactive quizzes about many different aspects of climate change. So I wanted to highlight this one that has to do with the frozen poles. So it's 10 questions to test your knowledge. So I hope that you will explore these tools and that you will have some fun with them. And that's it for me today. Thank you.
Thank you so much. So, of course, you want to be respectful of your time, and it is the end of the session. So for those of you who have to go, feel free to go. But for anyone who wants to stay and ask questions, or have a discussion, also free to do that. The Q&A box, maybe we should use that for more questions so we know what are questions and what are comments. So feel free to use that in the chat for any conversation.
So I'm just gonna, oh, okay, Laurel, you were doing some answering. So we will send out the presentation and it'll have all the links in it, and we'll also have supporting materials available. And those will come to you, anybody that registered for the workshop, that will come out through the climate school, and we'll work with them to get it to you. So you'll have all of this. Shall we copy the questions from the chat to the Q&A box? I was starting to get lost, to be very honest. I was trying to go back. And I think if you have something that you want answered that we haven't gotten to, that would be awesome if you wouldn't mind, because it gets to be a little bit nutty. I'm not sure. So Nicola asked what type of cameras took the initial images you were displaying at the start of the presentation. I'm not sure which images those would be.
Let me pull up the presentation. Maybe we can. Hold on one moment. I'm wondering if is it these series of images?
I'm not sure. These are, so that's a satellite image. The one underneath it that shows, that's created by something called Bed Machine, which consolidates a bunch of data from a variety of different resources. A lot of our radar data is used for this. Ice Bridge and other data has been used to compile this, but a lot of research. The next one is velocity, and that's from a combination of different satellites as well as ground measurements. So this was put together by science teams, and there are several versions of this that have been developed through the years. And then the last one is ice thickness, and most of that also will come from radar data, which goes through the ice. It'll image through the ice and hit the bed. And so we can get these different thicknesses. So those are combinations. So ISAT, we do have satellites that collect some of this data, but the images are actually pulled together. And if that's not what you were asking, Nicola, please help us understand better.
I think this is it, Margie. She said the different colored layers. Yes.
Okay. Yeah, and this is put together so that they fade into each other. So this is layered. So when you get this, you'll be able to kind of look at them. I think I find this a very powerful way of looking at data, to be able to actually kind of let it melt into each other so that you can see these different pieces. And I see that Matt is answering questions wildly as well. So Matt, I'm glad to have you here.
Okay, we have a question that says, is there volcanic activity in the area? Can we measure the temperature on the surface on which the glaciers are sitting? So I think the temperature of the bedrock under the ice.
So yeah, there definitely are studies that look at that. When I think of volcanoes under the ice, I actually think of Antarctica, where there are quite a few of them in West Antarctica, and there are definitely thermal measurements that are being collected. I don't know of, I should know this, I guess, but I really don't know that there are volcanoes up in the Greenland area. There might be. I don't know if anybody's on here that might know that besides me. But yeah, that's the best that I can tell you. I'm sorry.
Oops, sorry about that. I was trying to scroll in the Q&A. Okay, Carolyn has a question. We're hearing about polar amplification in Minnesota. Our winters are warming 13 times faster than our summers, as we are actually higher in latitude than most people think. My question is polar amplification the same at the northern and southern pole?
Yeah, so no, it's not. The northern hemisphere is seeing much more polar amplification than the southern hemisphere, which tends to, there's more land in the northern hemisphere, so that tends to have more heat with it. And like Antarctica is almost completely separated in terms of the Southern Ocean, and there's this Antarctic circumpolar current, which really kind of keeps it held separate from the rest of the world. There is certainly an exchange, but it does tend to be more isolated, whereas the Arctic region is really connected in every way with land and water. And then there's another main difference, which I'm sure you probably are all aware of, And that is that up in the Arctic, we have a large ocean that's covered with sea ice and then land that fringes it. Whereas in the Antarctic area, we have a big land mass that's covered with ice that's sitting for certainly the East Antarctic side is sitting up out of the ocean. West Antarctica is pushed down into the ocean, but you know, that's a big difference. So if you have this mostly water versus this land with ice on it, it's going to have less of a polar amplification situation going on. As we open up that Arctic Ocean, it's dark in color, and remember that whole conversation about reflectivity, it's absorbing more heat. And Nicola, bed machine, yeah. So there used to be a bed map, which was the compilation of data. Now there's a different version that's called bed machine. That is a group of scientists that work on compiling and putting together this data. And it looks like, is that all of our questions?
I think so.
Terrific. Well, thank you all so much for coming. It's always fun to talk about the polls. We like getting chill, as Laurel and I like to say. and we will be following up with more resources. So thank you very much.
Yeah, thank you guys. The recording should be posted on the website in the next week, and we'll send it around to everyone who registered. Thank you again to our panelists, and hopefully we'll see you all at our next session. And have a great rest of your days.